point is discrete Fourier transformation. So before learning Fourier transformation, let's see what is Fourier series. So if you are given any periodic function f, that means the value of the function repeats after a certain interval, then this is known as periodic function. The best example for periodic function are sine and cosine. So let us consider one sine function. So if you have this graph of a sine, then if you notice, then this part is repeated after an particular interval. So if this is 0, this is pi by 2, then pi, 3 pi by 2, this is 2 pi. So now after an interval of 2 pi, the sine function repeats itself. The values for the sine function repeats. Therefore this is known as periodic function. So if you are given any periodic function, then Fourier series is nothing but Fourier series is an infinite series representation of this periodic function f, and it is represented in terms of sine and cosine formula. We will see the formula for this and you'll get to know. So f of x can be represented as a0 by 2 plus summation n equals to 1 to infinity an cos of n pi x upon L plus bn sin n pi x upon L. Okay, so this is the transformation, or this is the conversion of a function, periodic function, into a Fourier series. Okay, so this can be represented in the form of cosine function and sine function, and this will give you an infinite series. So this is the Fourier series formula. Now what is this a0? So for this a0, there is one formula, 1 upon L 2L f of x dx. So what is this L? Basically it is the interval in which the function is located, that is minus L to L. Similarly, an is nothing but 1 upon L to L f of x cos of n pi x upon L dx, and bn is 1 by L integral 2L f of x sin n pi x upon L dx. So there is no need to by heart this formula. This is not in your syllabus. This is just a quite simple introduction to you. So this is what a Fourier series is. If you are given any periodic function, you can convert it in terms of an infinite series, which is represented in the form of sine and cosine. So another way of representing this Fourier series is what a0 upon 2 plus summation n equals to 1 to infinity an cos of 2 pi nt upon capital T plus pn sin 2 pi nt upon capital T. This capital T is nothing but the period, that is, if f of t is a function and if it is a periodic function, then this f of t plus capital T equals to f of t. So this is the period of that function. So omega naught, that is the frequency, it is given by 2 pi upon capital T. So now if you are given any periodic function and it is in a time domain, that is t, then it can be converted into a frequency domain. So conversion or transformation of a function from time domain to frequency domain. It is done with the help of a mathematical tool, and it is known as Fourier transformation. Okay, so basically it's a periodic function in the time domain, and you apply some formulas on this function to get to convert it into a frequency domain. So the formula for this Fourier transformation is nothing but f equals to integral minus infinity to infinity x of t e raised to minus I 2 pi ft dt. This is for the function which is a continuous function. So this formula is applicable for a continuous function, and similarly if you have a discrete function, then this is given by summation n equals to 0 to n minus 1 x raised to n into e raised to minus I 2 pi kn upon capital N. Okay, so this is for discrete, other one was for continuous. So let's see what exactly discrete Fourier transformation is. So now let us consider one omega. We know that omega is nothing but nth root of unity. So the value for omega is given as e raised to minus I 2 pi upon n. Okay, so this is the formula for omega. Now if we consider omega raised to n, then what you will get, e raised to minus I 2 pi upon n raised to n. So we'll have it as e raised to minus 2 pi into I. So it is in the form of e raised to I theta, so you can write it as cos of 2 pi minus I sin 2 pi. So this will be equal to cos 2 pi 0 minus minus 2. So it will be 1. So omega of n is equal to 1. Now what relation we have with respect to nth root of unity is 1 plus omega square up to so on plus omega raised to n minus 1 equals to 0. So on the next step we'll do is multiply both the sides by 1 minus omega. So what you'll get is 1 minus omega into 1 plus omega square plus up to so on plus omega n minus 1, which is equal to 0. So this will give you 1 into 1, the entire bracket as it is, minus omega into this will give you minus omega. So this minus omega and this omega will cancel out. Similarly all the terms will cancel, and what will be left is 1 minus omega raised to n, which is equal to 0. So you'll give 1 omega n equals to 1, and now replace omega by omega square in the above equation, that is the equation 1. Okay, so if we replace this, then what we'll get is 1 plus omega square plus omega square plus up to so on plus omega square raised to n minus 1, which is equal to 0. So this is one equation which we got. We can directly write it as omega square plus omega raised to 4 plus up to so on plus omega raised to 2n minus 2, which is equal to 0. Now if we replace this omega by omega cube, then what we'll get is 1. I'll directly write it down, that 1 plus omega cube plus omega raised to 6 plus up to so on, plus omega raised to 3n minus 3, which is equal to 0. Similarly, in this way, we can replace omega by all other powers of omega. So at the n minus 1 step, what you will get is, if we replace omega by omega raised to n minus 1, we'll get 1 plus omega raised to n minus 1 plus omega raised to n minus 1 square plus up to so on, omega raised to n minus 1 raised to n minus 1, which is equal to 0. Now what happens if we replace omega by omega raised to n? Then what we'll get is 1 plus omega raised to n plus omega raised to n whole square plus up to so on, omega raised to n minus 1. Now we know that omega raised to n is equal to 1. We have found it out in this equation. So substituting its value, we'll get 1 plus up to so on plus 1, which is totally n times. Therefore we can directly write it down as n. We got the relations of omega and its power. So we'll use it here and let's see what we get. So suppose if you have a vector x, so if it is denoted as x0, x1 up to so on, x n minus 1. So this is a vector representation and it is an n dimension. So if you have omega, which we know it as e raised to minus I 2 pi upon n, okay, so this is what we have. Now if we apply a Fourier transformation on this vector s, then it will be converted into some another vector. So suppose if this vector x, it is transformed into another vector y, which is represented as y0, y1 up to so on, yn minus 1 transform. Okay? So this is the vector representation where this y0, y1 up to so on, yn minus 1 are the vector components of that vector. So how you can calculate or how you can solve for this y? So we will need to find the vector components individually and then we can see that this is the required vector. So suppose yk is the general notation for this vector component, then this yk is given as summation j running from 0 to n minus 1 xj into e raised to minus I 2 pi upon n raised to kj. Okay, so now instead of e raised to minus 2 pi n, we can directly substitute here as omega, that is summation j running from 0 to n minus 1 xj into omega n kj. Okay, so now this k will go from 0, 1, 2 up to so on n minus 1. That means we have to find y0, y1 up to so on yn minus 1. Okay, now as this j is xj is nothing but component of x, so j will run from again 0 to n minus 1. So if we substitute value for k's, then if k equals to 0, then we'll get the first component, vector component, that is y0, which is equal to summation j running from 0 to n minus 1 xj into omega n raised to k is 0, so 0. So this will be equal to summation j running from 0 to n minus 1 xj into omega 0. Okay, so if we expand this summation, then what we'll get is y0 is nothing but x0 omega 0 plus x1 omega raised to 0 plus x2 omega raised to 0 plus up to so on xn minus 1 omega raised to 0. Okay. Similarly, if you put k equals to 1, then you'll get the second component, that is y1, which will be equal to summation j running from 0 to n minus 1 as it is, xj as it is. Now it will be is omega n raised to 1. Sorry, omega n raised to kj, that is k equals to 1, then it will be just j. So y1 will be equal to, if we expand this, then x0 omega 0 plus x1 omega 1 plus x2 omega 2 plus up to so on x n minus 1 omega n minus 1. So if we continuously substitute values for k, and finally the last one, that is n minus 1, you will get y n minus 1 will be equal to summation j running from 0 to n minus 1 xj omega n j into n minus 1. So this we will get as x naught omega naught plus x1 omega raised to n minus 1 plus up to so on x n minus 1 into omega raised to n minus 1 and this raised to n minus 1. So these are the components of the vector y, and if you want to represent it in terms of matrix, then you can say that this y0, y1 up to so on yn minus 1 can be written as the matrix multiplication of all the coefficient of this omega, so x0, x1, x2 up to so on xn minus 1. That is, if you consider this first case, then the coefficient of x0, x1, x2 up to so on xn minus 1 are omega raised to 0. So we will write this up to so on omega raised to 0. Then the second one is for k equals to 1, we got the coefficients for x0, x1 up to so on xn minus 1 as omega naught, omega 1 up to so on omega raised to n minus 1. Going in this manner, if you consider for n minus 1, then you got omega naught, omega n minus 1 to so on omega n minus 1 raised to n minus 1. Okay, so this multiplied with x0, x1 up to so on x n minus 1, that are the coefficients of, or that are the vector components of the vector, original vector x. Okay, so if you are given any vector x which is equal to this, then you need to use this formula to evaluate the vector transformation, and this is the process. We will see one example so that the concept will be clear. Okay, so if you are given one sequence, that is a vector which is xi equals to 1 1 0 0. Okay, so this is the vector given. So here capital N is nothing but the number of vector components, that is n equals to 4. Now to find the vector component after the transformation or after the discrete Fourier transformation, you know that the equation, the formula is yk equals to summation j running from 0 to n minus 1 xj e raised to minus I 2 pi upon m j k. Okay, so you know this formula. Then this will give you, if you n equals to 4, then you know that summation will go from j equals to 0 to 3 xj as it is. Now n equals to 4, so we'll get that e raised to I 2 pi upon 4 raised to jk, which is equal to summation j running from 0 to 3 xj. This 2 will get cancelled with this 4, so we'll get e raised to minus pi by 2 jk. Now if you consider this, then e raised to minus I pi by 2, this will give you just minus I. So this will give summation j running from 0 to 3 xj minus I raised to kj. Okay, so this is the modified formula for yk for this particular example. And now we will substitute values for k, that is y0 is equal to summation j running from 0 to 3 xj minus I raised to 0. So this will give you x0 plus x1 plus x2 plus x3. Okay, so you know values for x0, it is 1, x1 is 1, x2 is 0 and x3 is 0. So after substituting it, you'll just get 1 plus 1 plus 0 plus 0. That's nothing but 2. So if we consider k equals to 1, then we will get y1, which will be equal to summation j running from 0 to 3 xj minus I raised to k equals to 1. So it will be just j, which is equal to, now after expanding the summation, we'll get x0 raised to minus I raised to 0 plus x1 into minus I raised to 1 plus x2 into minus I raised to square, that is minus I square, plus x3 into minus I raised to 3. So after this we'll get x0 plus minus x1I minus I square, so it will become minus 1, so minus x2, and this will become minus x3I. So after substituting its value, we'll get x0 as 1, so 1 minus I plus 0 plus 0. So final answer is 1 minus I. Similarly, to find the third component, that is y2, we have to substitute k equals to 2. So summation j running from 0 to 3 xj minus I raised to, now this k equals to 2, so 2j, which will be equal to x0 plus minus I raised to 0 plus x1 minus I square plus x2 minus I raised to 4 plus x3 minus I raised to 6. So this will give you x0, so x0 into, so this will become x0 into minus I raised to 0, this will give you x0. Now this minus I square is minus 1, so minus x1, and this will give you x2 is 0 and x3 is 0, it will give you 0, 0. So x0 is 1 and x1 is 1, so this final answer is 0. Similarly, for the fourth component, that is y3, you will get summation j running from 0 to 3 xj minus I raised to 3j, which will be equal to x0 into minus I raised to 0 plus x1 into minus I raised to cube, that minus I cube, plus x2 into minus I raised to 6 plus x3 into minus I raised to 9. So this will give you finally 1 plus I plus 0 plus 0, which is equal to 1 plus I. So finally our vector is y, which is equal to, first component we got it as 2, second component we got it 1 minus I, third component is 0, and fourth component is 1 plus I. So this is our required vector after the transformation or after the Fourier transformation. This is the one way. Other way is by matrix formation. So we'll see this. So if you want to find y1, y0, y1, y2 and y3 components of vector y, you can directly solve it by matrix formation, and we know that the matrix of the coefficients for x0, x1, x2 and x3 are y is raised to 0. So it was just 1, 1, 1, 1, omega, omega square, omega cube. Then you have to raise the power of omega square, that is omega square, omega 4 raised to 4 and omega raised to 6. Similarly, you have to finalize omega cube, omega raised to 6, omega raised to 9 into x0, x1, x2 and x3. So this will give you 1 as it is. Now, what is omega? Omega is nothing but minus I. Omega square is nothing but minus 1, and omega cube is I. Omega raised to 4 is 1, omega raised to 6 is minus 1, and omega raised to 9 is minus I. So you need to substitute all these values in this equation, in this matrix. So we'll get omega value as minus I, omega square as minus 1, then omega cube as I, then this will come minus 1, I, 1 minus 1 minus 1 1, and you have to multiply it with 1 1 0 0. So this, after solving this matrix, you have to multiply the first row with this column. You'll get 1 into 1, 1 into 1. So addition of this, so 1 into 1 plus 1 into 1, that is 2. Similarly, you have to multiply this row with this and add the components. So you will get 1 into 1 is 1, minus I into 1 is minus I, then multiplying it with 0, it will cancel out. So now third component as 1 into 1 minus I, sorry, 1 into 1 into minus 1 into 1, so it will become 0. Then fourth component 1 into 1 and I into I is plus I. So this is the final answer after multiplication, and these are the components for y1, y0, y1, y2 and y3. So finally again you got the same answer as the required vector after the Fourier transformation. We'll see another one. So example, you have to find the DFT, that is discrete Fourier transform of the sequence 1 1 1, and it is an infinite sequence. So here what we can say that for any component of x, that is xj in general, we have its value as 1 for j equals to 0 1 2 up to so on and minus 1. So now to find the kth component of y vector, that is yk, we have the formula as summation j running from 0 to n minus 1 xj into omega n raised to jk. Now we can directly solve it with matrix, it's easy. So let's see how it goes. So we need to find y0, y1, and we don't know up till which value, so we'll consider it as y n minus 1. So this will be equal to 1 1 1 in 1 so again omega square, omega raised to n minus 1. So total it will be n cross n matrix, so omega square, omega raised to 4, and it will go to omega square raised to n minus 1. Similarly, going in this manner, omega n minus 1, omega n minus 1 to 2, up to so on, omega n minus 1 raised to n minus 1. So overall it will be n cross n matrix, and you have to multiply it with the components of vector components of x. So solving this, what you'll get is, so see, y0, y1 up to so on, yn minus 1 will be equal to, now if we multiply the first row with the column, then you'll get 1 plus 1 plus up to so on. As it is n cross n matrix, it is n times repeated, so you can directly write it over as n. And then if you see the second row, if you multiply it with 1, then what you'll get is 1 plus omega square up to omega raised to n minus 1. And we have already seen that the summation up till the power of omega as n minus 1 is 0. So you can directly write it down 0, and it will go continue to become 0. So this is the value for the vector after the transformation. What if you have a vector after a transformation, after a Fourier transformation, and you want to find the original vector, that is x. So to find that, you need to operate one tool, mathematical tool, that is inverse discrete Fourier transformation. So that is inverse DFT. Now the formula for inverse DFT, that is for the components of x, that is xj, you have to use the formula 1 upon n summation k goes from 0 to n minus 1 yk e raised to I 2 pi upon n raised to jk. Okay, so this is the formula for the inverse DFT. That means if you are given a component or a vector after the Fourier transformation, and you have to find the original vector. So now this 1 upon n is known as normalizing factor. So now what are the properties of DFT, and this we'll see after one example. So let's see one example based on inverse DFT. So if you are given a vector yk which is 1 0 1 0, okay, so this is the vector after a Fourier transformation. You have to find the original vector. So here if you count, then n equals to 4. So to find the original vector xj, which will be equal to 1 upon n, that is 1 upon 4 into summation k goes from 0 to n minus 1, that means n 0 to 3 yk, and if you substitute here e raised to 2 pi upon n I as omega, then directly you'll get this answer as summation yk omega raised to minus jk. Okay, so this will give you directly omega raised to minus jk, where the value for omega will be e raised to minus I 2 pi upon 4, which will be equal to e raised to minus I pi by 2. Now e raised to minus I pi by 2 will give you the answer minus I. So this you can directly substitute the value. So you will get x naught, which will be equal to 1 upon 4 into summation k running from 0 to 3 yk omega raised to 0, which will be equal to 1 upon 4 y0 plus y1 plus y2 plus y3. So you know values for y0, y1, y2 and y3 which are 1 0 1 0. So after substituting it, you'll directly get the answer 1 by 2. Similarly for x1, you'll get 1 by 4 summation k goes from 0 to 3 yk omega raised to, now minus j, k equals to 1, so directly minus j. So this will be equal to, value for omega is nothing but 1 upon 4 y0 into omega is minus I, so minus I raised to 0 plus omega, sorry, y1 minus I raised to minus, so this was minus j, so minus 1 and into 1, so minus 1 plus y2 into minus I raised to minus 2 plus y3 into minus I raised to minus 3. So this will give you 1 upon 4 into y0 is 1 plus 0 into minus I raised to I, doesn't matter, plus 1 into minus I raised to minus 1, so minus I raised to minus 2, this will directly give you minus 1, and y3 is again 0, so final answer will be 1 minus 1, so 0. So now if you want to find value for x2, then similar process, 1 by 4 summation k goes from 0 to 3 yk omega raised to minus k, sorry, it is minus k, so because k goes from 0 to 3, so value, so the variable is k. Now this will give you 1 by 4 into x0, sorry, y dot into minus I raised to 0 plus y1 into minus I raised to minus 2 plus y2 minus I raised to minus 6 plus y3 into minus 4 into y3 into minus I raised to minus 6. So after substituting, you will get the final answer 1 upon 4 y0 into this, so directly y0 plus y1 is 0, so 0 plus y2 is 1, so y2 into minus I raised to minus 4 equal to 1 plus y3 into minus I raised to 6, y3 is again 0, so directly you can write 0, no need of calculation. So we'll get the answer, y0 is 1, y2 is 1, so it will become 1 by 2. The last one, that is y3. So to find x3, 1 by 4 summation k goes from 0 to 3 xk omega raised to minus 3k, which is equal to 1 by 4 into y0 omega raised to 0 plus y1 omega raised to minus 3 plus y2 omega raised to minus 6 plus y3 omega raised to minus 9. So after substituting its value, you'll get 1 by 4 into y0 plus 0 plus y2 into omega raised to 6. So So omega raised to minus 9, which is minus 1. So this will become 1 upon 4 into 1 minus 1, which is equal to 0. So the final original vector is 0 0.5, 0, 0 0.5, and last one is 0. So another method by matrix, you have to just use the matrix as x0, x1, x2, x3 equals to, now we have to multiply it with omega, omega square, omega cube. So instead of this, you have to just use the minus sign, that is raised to power minus n, that is omega raised to minus 1, omega raised to minus 2, omega raised to minus 3, omega raised to minus 2, omega raised to minus 4, omega raised to minus 6, omega raised to minus 3, omega raised to minus 6, omega raised to minus 9 into y0, y1, y2, y3. So after solving this, you'll get again the same answer. Okay. So there are a few properties of DFT, that is linear property. The first one is linear. So if you have two vectors, suppose x1 and x2 are the two vectors, and if you add these two vectors first, and then if you operate the mathematical tool, that is DFT, that is Fourier transform, then after transformation you will get certain value, that is DFT of x1 of j plus x2 of j. So these are the two vectors x1 and x2. So first you will add those, and then if you operate the transformation, then you will get the similar answer by just having the vector x1, applying the DFT on that. So after applying the transformation, x1 will give you y1, and after applying DFT on x2, you will get y2. So if you individually apply the transformation on x1 and x2, you will get y1 and y2 respectively. And if you add this vectors after the transformation, you will get the similar result as in the first case, that is first adding the vector and then applying the transformation. So this is known as linearity property, and DFT follows it. Okay. Second one is periodic property. Periodic property is nothing but if yk is a DFT, that is a transformation of vector xj, then what you can say is y of k plus n equals to yk. So this after a point, so if there is an interval or a period of n, then the Fourier transformation has a periodicity. So it repeats after a certain period of time. So we are left with the last point, fast Fourier transform. We will take that point afterwards. So next we will start our unit 2,